This is a supplementary video for our work on automatic cutting and flattening of carotid artery geometries. For research on cardiovascular diseases such as atherosclerosis, it is important to understand the impact of different parameters on the vessel walls. These can be measured values such as wall thickness or plaque occurrence, but also values derived from hemodynamic simulation such as wall shear stress. Visual exploration of these values can be cumbersome, especially if they are temporally resolved, as the viewer can only ever see one side of the geometry and multiple branches may overlap and occlude each other. We propose a new method to cut and flatten such vascular trees, which then results in a flat depiction or map of the vessel surface. Our method is fully automatic and requires only the geometry and optionally also surface data fields as an input. Our goal is to retain the original shape and area of the vessel as accurately as possible, and the mapping is intuitive in a way that it's easy to mentally reconstruct the flattening. For this, we propose natural vessel cuts, which follow the minimal principal curvature of the vessel. And in contrast to other methods like minimizing geodesic distance, these cuts do not wrap around the vessel, but they stay on one side. After the cut, the geometry is flattened with a layout prior that we read from the cutting paths. And then we restore the area and proportions of the mesh. As a demonstration, we deployed our method with this tool, which can be used to investigate results from blood flow simulations within the carotid arteries. Here, the user can interact with a vessel geometry and map any required data fields onto the surface. If the data is temporarily resolved, the time can be set or animated. Now, to flatten the mesh, the user can first initiate the cutting, which takes the current view position into account and then computes a natural vessel cut. The cutting automatically detects inlets and outlets and creates a minimal number of cuts that connect at branch locations of the mesh. It ensures that the mesh is cut to a topological disk that can be flattened to the 2D domain through surface parameterization. If satisfied with the cut, the user can invoke the flattening and the result is displayed on the right. Now we can see the full surface at once, including any data fields. With a more complex mesh, the advantages of this method become obvious. So usually you would only see parts of an interesting parameter distribution and you would need to rotate the model, which is tedious if you want to explore multiple points in time. Now, if you cut the mesh, you will see the natural vessel cuts automatically find the dominant branches on which these main cut lines are created. And the cuts on the smaller branches then connect to the closest cut they can find. When flattening this mesh, we can then assess the whole domain at a glance. This can be used to identify regions of interest, and since we retain the area, the 2D view already gives an accurate impression of the size of interesting distributions. Now, this is not required, but if you wish to change the angles used in the flattening initialization, you can also do that. This shows that the method allows some control over the layout, which can be useful if you were to, let's say, create flattenings of different geometries and wanted to compare them. This is also a good demonstration of the fact that the cutting and flattening are independent, so we don't need to recompute the cut every time. If you wanted to change the cut, for example, to cut the mesh from the other side, it's as easy as choosing a new viewpoint and then reinitiate the cutting. If you flatten the mesh again, you can see that the 2D depiction changed its orientation to match the 3D layout, which facilitates easy mental mapping between the two representations. This tool is currently in use for the investigation of patterns in wall parameters of blood flow simulations that focus on human carotid arteries with stenosis. The aim of this research is to better understand the progression of stenosis and the impact of different stresses on the vessel wall. However, natural vessel cuts and the flattening we propose can be applied more generally to any vascular tree of similar complexity as the carotids. This also includes arterial trees with aneurysms, for example. Our method supports any number of outlets and any branch configuration and will work with different mesh resolutions and section sizes.